This lecture is about the nucleophilic addition to aldehydes and ketones, particularly carbon-carbon bond-forming reactions. Aldehydes and ketones have two types of reactivity. The first is based on the electrophilicity of this carbonyl carbon, and so it can undergo nucleophilic addition at the carbonyl carbon. It forms a tetrahedral intermediate, which upon workup gives the protonated alcohol. The second type of reactivity is based on the acidity of the proton at the alpha position. This is the alpha position, and the alpha position proton is acidic with a pKa of about 20 for aldehydes and ketones, and about 25 for esters and amides, and other carboxylic acid derivatives. Upon treatment with a strong enough base, this proton can be deprotonated to form an enolate. This is an enolate, and it has a resonance form which shows that the reactivity of this compound is at the alpha position, and it is nucleophilic at the alpha position. So upon treatment with an electrophile, this enolate can react, attack the electrophile, it reforms the carbonyl in this process, and adds on the electrophile. Now we're going to focus on nucleophilic addition reactions of aldehydes and ketones, in particular carbon-carbon bond-forming reactions. We've already looked at organometallic reagents such as Grignards, organolithiums, and Gilman reagents. And we know that all of these can undergo nucleophilic addition to the aldehyde or ketone. Now we're going to look at cyanide attack to form a carbon-carbon bond, and the Wittig reaction. The Wittig reaction makes use of a phosphorus ylide, which we'll look at in closer detail. We can treat an aldehyde or a ketone with cyanide, for example potassium cyanide, and have nucleophilic attack of the carbon onto the carbonyl of the ketone or aldehyde. In this case, we're going to form our tetrahedral intermediate, we have now formed our carbon-carbon bond. This is our new carbon-carbon bond that we have made, and upon workup with mild acid, we can protonate that alcohol. This functional group is called a cyanohydrin. Nitriles have an electrophilic carbon attached to the nitrogen. They are very similar in reactivity to all the carboxylic acid derivatives, and upon treatment with strong acid, water, and heat, they can be converted to the carboxylic acid. On treatment with strong reducing agents such as lithium aluminum hydride, nitriles can be reduced to the corresponding amine. Due to the presence of this electrophilic carbon, they can also undergo nucleophilic addition. Cyanohydrins can also be dehydrated to form the alpha-beta unsaturated nitrile. Treatment with tosyl chloride or mesyl chloride with pyridine converts this alcohol to a good leaving group, followed by elimination using the beta proton. We can form the alpha-beta unsaturated nitrile. This is the alpha position, this is the beta position, and that's where the new alkene is formed. These compounds can undergo similar reactions to alpha-beta unsaturated carbonyl compounds. The Wittig reaction is the reaction between an aldehyde or ketone with the Wittig reagent to form an alkene. You can see that in this compound, we replace the carbonyl oxygen with this group of the ylide. The Wittig reagent is a phosphorus ylide, and ylide is any species that has a positive and negative charge on adjacent atoms. A phosphorus ylide has a phosphorus in the ylide. The groups attached to the carbon that bears the negative charge does not necessarily have to be hydrogens. They can be any R group, and this introduces the possibility of Z and E isomers of the alkene. For simple ylides, you will favor the Z alkene. For structurally complex ylides, you will get a mixture of E and Z. The Wittig reagent preparation starts from triphenylphosphine. Triphenylphosphine does an SN2 reaction with the corresponding alkyl halide, and that means that the alkyl halide should be primary or secondary, and gives this phosphonium salt. This salt has a pKa of the alpha proton of about 22. This acidic proton can now be deprotonated by a strong base, such as N-butyllithium, to give the ylide. The ylide has two resonance forms, where we can draw it as a double bond between that carbon and phosphorus, or more realistically, the carbon is bearing the negative charge and the phosphorus bearing the positive charge. This is the Wittig reagent. The mechanism of the Wittig reaction starts with the attack of the ylide onto the carbonyl. The carbon of the ylide can attack the carbonyl carbon in a nucleophilic addition to form the tetrahedral intermediate. This compound can then undergo attack of the oxygen on the phosphorus to give us an oxaphosphatane. An oxaphosphatane has a four-membered ring with the phosphorus, oxygen, carbonyl carbon, and the ylide carbon. This is called the oxaphosphatane. And an alternative mechanism can go directly from these two compounds to the oxaphosphatane if there was a concomitant attack of this carbon on the carbonyl followed by this oxygen on the phosphorus. Once the oxaphosphatane is formed, it then collapses to form the alkene and produce triphenylphosphine oxide. So the organic product of the reaction is the alkene. Remember, for simple ylides, it'll favor Z. In this particular case, since you've got the same group on either side, this is neither E or Z. And the side product is triphenylphosphine oxide. Triphenylphosphine oxide is the driving force of this reaction, and that's because it forms a very, very stable phosphorus-oxygen double bond. Now pause the video and predict the major product or missing reagent for each reaction. If we look at the first compound, we've got several functional groups. The TIPS group is shown here. It is the triisopropyl silyl group. It's a silyl protecting group for this alcohol. Overall, in this reaction, we are converting an alkene to an epoxide, and nothing else changes in this reaction. And so we can use any epoxidizing agent, such as hydrogen peroxide. In this case, I'm going to use tert-butyl hydroperoxide. Once we have the epoxide in place, we are treating this compound with the Wittig reagent. So we are doing a Wittig reaction with this carbonyl here. And so that's going to convert it to an alkene. And after that, we are treating it with TBAF. TBAF is going to deprotect the silyl protecting group, and so we're going to convert this protected alcohol to the free alcohol. So our compound, our final product, is going to be with an alkene, everything else still in place except for the deprotected alcohol.